All right, welcome back everyone. And in this video, we are continuing our mechanics of material series and dealing with normal strain. And strain is really essentially the deformation that accompanies a stress, right? You know, you're stressed, so you feel strained. You talk about feelings all you want. Oh, I feel so strained because I have so much stress. It's like terms we use every day, but we're gonna use them in an engineering sense. You know, if you like look at a rubber band and you apply a force to that rubber band, you can see it elongate, and then you can even see the cross section shrinking, which is something called Poisson's ratio that we're gonna deal with later. And but sometimes, a lot of times, you can't see this deformation. You know, when you put books on a bookshelf, you can't really see the bookshelf sagging unless you have lots of books and you overloaded it, and maybe you bought the bookshelf from IKEA, the cheap one, the Billy bookcase, right? Anyway, so the so here, the idea is that we want to look at the deformations associated with various loading, and those loadings cause stress, and those stresses induce strains. And sometimes we want to look at it backwards. We want to be able to experimentally measure the strains and see what kind of stresses are caused, and find out whether or not it exceeds an allowable limit. Okay, and just like in stresses, just like there are two types of stresses, there are two types of strains. There are normal strains that are accompanied by normal stresses, normal strains, and shear strains from shear stresses. Okay. And here in this video, we're going to deal with normal strains mostly. We're going to describe them, and then hopefully you can figure out or explain how to calculate them. And the shear strains we'll deal with another video. But let's take, for instance, an axially loaded bar. Okay. So here I've got this. Let me take an axial member or a bar here that's fixed to a wall like this right here, like that, and it's got some length. Say it has a length here of L0, and then I'm going to apply slowly a static load. I'm going to apply very slowly, quasi-static, if you were doing this experimentally right here, right? I'm going to apply this very slowly, a load here that causes a deformation, okay, that stretches this bar here. So here, bam, this P, I have this applied load here, and I end up with this final length. This final length, LF, I'll call that the final length. And you would say the change in deformation, we'll call this little delta, lowercase delta, the change in deformation is equal to the final length minus L0. And that would be indicated by, on here, this distance, delta, the change in length. Okay, and the definition of the normal strain, or the strain here, is not, it's not just it deformed this distance, but it's going to be kind of the rate or the change in length per unit length. Okay, so here, this normal strain, which we use the symbol epsilon, which is typically, again, uses the symbol epsilon here. This is my the way I write Greek epsilon right here, is the change in length divided by the original length right here. And this is my normal strain. Okay. And the way I've done this for an axially loaded bar, this gives us a really good feel for the average strain across this element. But sometimes, our loading is not so concise. It's not always just one direction. And what happens is that, you're loaded, you have loading in multiple directions going on, and you have this deformation. Just think of a ball or a beam that's being loaded transversely and pulled and torqued, okay, all at once. And so you want to be able to evaluate the longitudinal strain, or the normal strain, excuse me, the normal strain at a point, okay? And so in order to do that, we look at line segments. And so let's take, for instance, I will draw, let's say, a line segment here. So here I want to study this line segment. I'll call this point A, point B. It has an initial length here, this line of delta S, okay, this delta S, and this is, and really, on a large structure, the distance between A and B to us would look like a dot, okay, a really tiny dot on a structure. And so, but I'm magnifying it here just for, for the purpose of seeing it. And what happens when I apply this load right here is that point A which will have been here, will move down a certain distance to a new position here, which I will say move the distance u, okay, and this will be this new A prime. That's this new location. And then point B might move, it used to be, oh, excuse me for making it so, here, let me correct this a little bit just to make sure that we make this clearer. So let's say point A, the new one is right here. We'll call that delta U. Okay, I'm sorry, U, a distance U right here. Okay, this distance U, and this is A prime, this new A prime right here. And then point B moves down a distance U plus another distance. Okay, so here is the original point B location. This is the new B prime. Here is that U. And then here is this other distance, which I will call delta U. Oops, delta U. And we would say here, and here's and this new line segment right here, delta S prime right there. Okay, that delta S prime. And I would say, well, the strain, the normal strain of this region, of this location, this line segment, is going to be just like before, the change in length, which will be the delta S prime minus delta S over the original length delta S, which in terms of these delta U's and U's, this delta S prime, so if you look at it, it's really just this delta U divided by delta S, okay? And this would be my average normal strain for segment AB. AB. And really, because we're studying, large bodies, and when I say body, I'm talking about like a beam, or it could be a computer monitor, whatever, right? Something that has an applied load to it, a building, okay? And how a lot of times we want to look at a point, at a specific point on the body, and so that means that this line segment becomes infinitely small. It goes small, right? It gets small. It gets closer and closer to zero. So this delta S gets closer and closer to zero. So, as you can imagine, there's some limit as delta S goes to zero of delta U over delta S, which becomes a derivative, du over ds. And that says that this is my normal strain at a point of body, okay? But this derivative application is really, we're not going to be using this until later, okay? A little bit later, so a little bit later on. Right now, we're going to be sticking with kind of this definition. Like, I would say this is probably the most useful definition and the best way to calculate our normal strain of a segment, a point, okay? And when the strain is positive or greater than zero, we're going to say that that's associated with an elongation. And when the normal strain is less than zero or negative, we're going to associate that with contraction in terms of sign convention. Another thing you always want to be aware of are the units. And the units for this, if you look at this, is dimensionless, okay? So the units of normal strain, it's dimensionless. And what's typically used, dimensionless. And what's typically used is it's common to write, the units as, length over length. So things would be like meter per meter, or inch per inch, or that would be it. Sometimes this thing is expressed as a percentage. A lot of times, because these strain values are so small, you might use, so let's take, for instance, a number. Let's say you have done something, you've done some work, you had a strain gauge on a beam or something that was loaded, and you found a strain value of 480 times 10 to the minus 6, dimensionless, some number, 480 times 10 to the minus 6. Okay, this was a strain. This was a normal strain. You could say this is the same as 480 times 10 to the minus 6 inch per inch. Or you could say it's the same as 480 times 10 to the minus 6 meter per meter, or millimeter per meter. Okay, or 480 times 10 to the minus 6 meter per meter. If you wanted to express this as a percentage, this would be, you're going to multiply this by 100, okay? This would end up being 0.0480%. And again, this is all equivalent. And sometimes, because this 10 to the minus 6 actually occurs a lot, okay, a lot of times it's even expressed this way, we might say it's 480 micro inch per inch. And this micro is just another way to say 10 to the minus 6. Or we might say 480 micrometers per meter. Okay. Or microstrain, I'm sorry, micro. And so another way to call this is microstrain. Okay. So that's just another way to do it. And these are some of the units. And hopefully you got a feel for normal strain, how it's calculated at least. And then, we'll do some example problems later on. All right, and get ready for the next video on shear strain. Woo! Later.